Hi, I'm Michaela Torbett, Math 241, Section 12, and today we'll be discussing what it means for a surface to be smooth and how to find its surface area. A surface R is said to be smooth if its partial derivatives with respect to u and v are continuous and the partial derivatives when crossed with each other do not equal the zero vector for all uv in the domain of R. Then, if these things hold true, we can define its surface area to be from a one-to-one smooth surface from a type 1 or 2 region in D in R2 to R3. Then the surface area of the range of R is said to be the double integral of the magnitude of the cross products of R's partial derivatives with respect to area. We will now be looking at an example of a smooth surface R satisfying the conditions that D is equal to a square subset. Every grid curve in R must be a circle, and R begins with a counterclockwise rotating unit circle and ends with the unit circle rotating clockwise. So for this, I chose a piecewise function containing 3 pieces, each of which are half of a tori. My subset D is the region with u bounded from 0 to 2 pi and v bounded from 0 to 3 pi. For this, I found the center and the path in which a circle will move, and then I parameterized that circle, the unit circle, so that it moves beginning with in a counterclockwise rotation. And here you can see the steps that I followed to make such a surface. Here is the 3D rendering of my surface R. We know that for a surface to be smooth, its partial derivatives must be continuous and their cross products must not be equal to the zero vector for all uv in the domain of R. So I've calculated the partial derivatives of each piece of the piecewise function, and we found that they are continuous, and this is because the sine and cosine functions are continuous by themselves, so when multiplied or add or subtracted from each other, you're still left with another continuous function, making all of these partial derivatives continuous. So now we can check for their cross products. Here we have the calculations for the first and second pieces of the function, and we can see that the cross products of each of the partial derivatives are never going to be equal to 0 for all of uv in each R. And that's because cosine and sine will never be 0 for the same u and v values at the same time. So when they're added or subtracted together or multiplied, we can still see that they'll never be equal to 0, to the zero vector. And here are the calculations for the third partial derivatives of the third piece of the function. And once again, these are also not equal to 0, to the zero vector for all uv in R3. So we have determined that the partial derivatives of this surface are continuous and that their partial derivatives when crossed together do not equal to the zero vector. But there's one more thing we have to check for smoothness. We can see from looking at the surface that it's going to be smooth, that all of the lines line up, but since it's a piecewise function, we have to check the partial derivatives at the boundary points. And so here are 2 computations of those boundary points. We can see that when v is equal to pi, then R1 and R2 meet, and since the partial derivatives of them are equal to each other, we know that it is smooth at that point. And so moving forward, we can check the boundary point between R2 and R3 of our surface, and once again we see that these are equal to each other, making this a smooth surface. So now we can compute its surface area. Since we determined that the surface was smooth, we can now compute the surface area. So R1, R2, and 3 are all parts of a torus. And the surface area for a torus is given by the equation 4 pi squared times r, where big R is the radius of the large circle of the torus, and the little r is the radius of the inner circle that's rotated within the large one to produce the torus. So computing all of the pieces of our surface, we got that the total surface area was 118.44 square units. So in conclusion today, we discussed what it means for a surface to be smooth, and then we denoted that if that surface is smooth, we can then find its surface area by computing the double integral of its partial derivatives crossed together. We then looked at a really neat example in which a surface begins with the unit circle moving counterclockwise and ending moving clockwise, in which all of its grid lines are circular, and it's from a square subset. And we then computed its surface area and found that it was 118.44 units squared. Thank you so much.